Hello, welcome to this video tutorial on Oracle's DTrace technology for Oracle Linux. DTrace is a comprehensive dynamic tracing facility originally developed for Oracle Solaris but is now available with Oracle Linux. You can use DTrace to explore your system and to understand how it works, to track down performance problems, or to locate the cause of abnormal behavior problems. This tutorial covers installing the DTrace packages from the Unbreakable Linux Network, the ULN, loading DTrace kernel modules and listing DTrace probes, some simple command line based examples, DTrace scripts, and where to get more information, that is the DTrace guide and the DTrace tutorial. For this tutorial I'll be using a virtual machine in Oracle VM VirtualBox. I have Oracle Linux 7.1 installed on this VM. The UEKR3 is loaded, version 3.8.13-98.4.1. and the system is registered with ULN, and I am currently subscribed to 3 channels on ULN: the OL7 DTrace user space channel, the OL7 UEKR3 channel, and the OL7 latest channel. I'm going to open up a browser and show that I'm already logged into ULN. The system name is OLN DTrace. I'll click on my system name to manage my subscriptions. I'll scroll down and you'll see that I am subscribed to these 3 channels: the user space, DTrace user space tools, the UEKR3, and the OL7 latest channel. I'll click on the channels tab. Then I'm going to click on the release drop-down list and select Oracle Linux 7 and scroll down to the DTrace user space channel, and you'll see that there are 2 packages. So I'll click on the link to those packages and notice the DTrace utils package. This package contains all the DTrace utilities and needs to be installed on our system. If I go back to a command line window and run an rpm-qa and grep for DTrace, you'll see that the DTrace utils package is already installed. And once you're subscribed to ULN, you can just run yum update or yum install to install that package. I'm going to go back to the ULN web interface and select another channel. Select the UEKR3 channel, and you'll see that it has 44 packages associated with it. So I'll click on the 44 link, and here you can see all the DTrace module packages for the different kernel versions. You can also scroll down at the bottom and you'll see some additional packages on the list. There's a DTrace module shared headers and a live DTrace-CTF package, and these are installed already, as you can see in the terminal window from the output of the RPM command. And if I run uname-r, it shows me the kernel version, and then I need to have the DTrace modules for that particular kernel version installed, which I do. And if it's not installed, if you run a DTrace command, it will download the package and install it automatically, or you can use the yum install and just install it directly. I'm going to go back to the command line here and do a list of a directory. /lib/modules/ whatever the kernel version is, /kernel/drivers /DTrace, and you can see the kernel modules are installed in this directory. There are 7 of those. You don't need to install the DTrace, the DT kernel modules. Those are for internal testing, but you do need to install the fast trap module using the modprobe command, and install the profile module and the SDK and the systrace. The DTrace module gets installed automatically by installing one of these other 4 kernel modules. If I do an lsmod command and grep for DTrace, you'll see that DTrace module is installed. I'm going to list some DTrace probes for all the providers, and to do that use the DTrace-L command for list, and it shows all the providers, all the probes for all the providers. Probes are tracing points or instrumentation points that enable you to record data at various points of interest. Each probe has 4 fields: a provider, a module, a function, and a name. And when you reference these probes, you have to use colons to separate those 4 fields. If you want to see the probes for a specific provider, use the -P and give it the provider name. So here's the DTrace probes, and here's the syscall probes, and there are a lot of syscall probes. If I pipe that to word count -L, you'll see the number of syscall probes, and if I count the total number of probes, you'll see that the majority of the total number are syscall probes. I can also show you the just a list of all the proc probes and the profile probes and the sched probes and finally the IO probes. Now I'll run some DTrace commands to enable these probes. To enable all the probes for a specific provider, all you need to do is remove the -L, the list option. So that command there enables all the probes for the DTrace provider, and it shows the begin probe, and then I do a Control-C and it shows the end probe. It shows you the CPU that the probe, where the probe fired, the unique identifier, the function name, and the probe name. The function name is nothing in this case. I can use the -N option and give a particular or a specific probe name, and the name I gave it in this example is DTrace : begin. Remember, you need a colon to separate each of the four fields: the provider, the module, the function, and the probe name. I can add an action. I can specify an action. The action in this example is trace. And what I'm going to do is display hello world. Trace is the most basic action, where it just takes an expression as an argument and traces the result to a directed buffer. Notice the trace. Notice the action is surrounded by curly brackets and terminated with a semicolon and quoted around the whole string. If I add another trace, which is exit, another action which is exit, then it exits without me having to hit Control-C. I can add a -Q for quiet, and then it suppresses all that CPU and ID and function and name information, and just gives you the output of the action of the trace command. The next DTrace command traces the time of entry for each system call. The provider is syscall. There's no module name, no function name. The probe name is entry. The action is trace, and the argument is timestamp. Timestamp is a built-in D variable that gives the current value of a nanosecond timestamp counter. I'll issue the command. I hit Control-C to exit, and the output shows the function name, the probe name, and the timestamp. And I'll repeat the command so that you can see it. Now I'm going to open up a second window where I can run some Linux commands which will generate output for the remaining DTrace examples in this video. The next DTrace command displays commands that are executing on your system. The provider is proc. There's no module name, no function name. The probe name is exec. The action is trace, and the argument is string of arg0. The string of operator is a D keyword which converts the operand to a string. All these keywords are described in the DTrace guide, which I'll reference at the end of the video. So I'll initiate the command. I'll go to the second window and run a man ls to generate some output. Quit out of that, come back to the first window, and you'll see the output, the function name, the function, the name, and then the command that is executing on the system. I'll repeat the command so that you can see again what I ran. The next DTrace command displays new processes with timestamps and command line arguments. The provider is proc, no module name, no function name. The probe name is exec-success. The action in this example is printf. Printf allows for formatting. The parameters consist of a format string followed by arguments. The arguments are timestamp and a pointer to the struct psinfo, which again is described in the DTrace guide that I'll reference at the end of the lesson. The second argument provides the initial command line arguments. So I'll initiate the command. I will run man ls in the second window to generate some output, quit out of that, and then Control-C to quit. And you'll see the timestamp is shown, the function name, the probe name, the timestamp, the process, and the command line arguments. The next DTrace command displays files opened by each process. The provider is syscall. There's no module name, I'm going to specify open star as the function name, and this will include all functions that begin with OPEN, and the probe name is entry. The action again is printf. The arguments are exec name and copy in string arg0. Exec name is the name of the current process's executable file, and copy in string is a D subroutine, which is described in the DTrace guide reference at the end of the video. So I'll initiate the command after I get all my changes made. Then I'll go to the second window and run man-s to generate some output. Hit Q, the output. Go back to the first window. Again, here we show the output, the function, where the probe fired, the probe name, the process, and the files opened by each process. And there's the command again. The next DTrace command displays the number of system calls by system call using aggregations. The provider is syscall, no module name, no function name. The probe name is entry. The action in this example is a num aggregation. All aggregations, num in this example, are prefixed with an @ sign. Probe func is a D built-in variable which provides the function field of the current probe. Count is a function name whose result is the number of times called. I'll run man-s, quit out. When you use aggregations, no output is shown until you press Control-C, and then the output is shown, which in this case is the number of system calls by each system call. The next DTrace command counts the number of write system calls and the number of read system calls. This example uses two probes. The first provider is syscall, no module name. The function name is write, the probe name is entry. Then I'll use a comma to separate the two probes. The second provider is syscall, no module name. Function name is read, probe name is entry. This command also uses aggregation, as indicated by the @ sign. String join is a D subroutine, which is described in the DTrace reference at the end of this video. I'll run man-s again in the second window to generate some output. Then I'll quit out of man-s, and I'll come back and show the output, which is the number of write system calls invoked by processes and the number of read system calls invoked by processes. This last DTrace command aggregates the number of read system calls but uses a predicate to exclude the read system calls initiated by the DTrace process. Predicates are expressions that are enclosed in a pair of slashes that are evaluated at probe firing time to determine whether the associated action should be executed. The predicate in this example is that the current process's executable file is not equal to DTrace. FDS is the files that the current process has opened in a file info_t array. File info_t is described in the DTrace guide, and fi_path name is the full path name. So all these arrays and predicates and aggregates and variables and subroutines and all these type of things that I'm using are described in the DTrace guide that I'll point out at the end of the video. I'll go to the second window and run man-ls, and again with aggregation you don't get any output until you hit the Control-C, and my output here is the process name, the full path name of the file that the process had opened, and then number of read system calls invoked by processes. I'm going to run some DTrace scripts. Each script ends with a .d suffix. I have some scripts already created. This first script shows quantized results for buffer sizes used in read sys calls. It gives a statistical breakdown of the sizes passed in the read sys call. This can be useful to see what buffer sizes are commonly used. Quant size is a D aggregating function that is described in the DTrace guide. Use the DTrace -s option to run this. Because the script uses aggregation, no output is displayed until I terminate it. And this shows the 256 is the most common buffer size used read in system calls with 37 instances. The next script counts system calls over a 10-second period. The script name is syscall.d. The script increments a counter and then exits after a count of 10 seconds. Use the DTrace -s command to run this. Because the script contains the exit action, I don't need to press Control-C. I just need to wait 10 seconds. The output will show the number of system calls by system call. And there you go. And I'll show the contents of the script again before continuing. The next script records the time that processes spend invoking read system calls. The script name in this example is arttime.d. This script stores the value of a timestamp to a thread local variable when it enters the read system call and then subtracts that value from the timestamp when returning from that read system call. Thread local variables are described in the DTrace guide. The script uses the printf action to format the output, and you can see there the executable file name, the time spent in each read system call in nanoseconds is the result of this script. And the last script shows the details of block I/O events. And this script uses enumeration, which associates a set of integers with a set of identifiers called enumerators that the compiler recognizes and replaces with the corresponding integer value. I'm going to run some fdisk commands in the second window so I can generate some block I/O output. And you can see there that it's already starting to generate some output just by listing the devices. I'll go ahead and partition a device, and more output is being generated in the background. Accept all the defaults and write it. Come back and see the output again. The output includes the CPU where the probe fired, the unique probe ID, the probe name, the device name, the probe name with a timestamp, the executable file name, the block size, sector number, so forth. This concludes the DTrace video demo. Visit the URL referenced on the page here. And the DTrace guide describes the deprogramming language, aggregations, subroutines, built-in variables and functions, pretty much everything you ever wanted to know about using DTrace. The tutorial gives examples about tracing operating system behavior, tracing process creation, tracing system calls, tracing user space applications, and many other examples. Thank you for taking the time to watch this video.